Thanks for your kind introduction. I'm Yang Liu, a postdoc from EPFL in the Laboratory of Photonic and Quantum Measurement, a group led by Professor Kippenberg in EPFL. So I slightly changed the title, but it's the same like a content for this talk. So I'm going to talk about our recent work on the photonic integrated circuit-based Erbium-Doped amplifier that can give you more than 100 milliwatt on-chip power. Okay, so at the beginning of this talk, I would like to motivate this talk by introduce the optical communication network development over the last 30 years. So as we can see, over the last 30 years, we have really seen a huge increase in the transmission capacity for the optical communication network. So with the invention of the erbium-doped fiber amplifier invented in mid 1980s, we are able to amplify the broadband optical signal in the different channels and allow us to compensate the optical loss in the communication link. So in the end, we can transmit a lot, a larger volume of data over the long distances, such as thousands of kilometers across the different continents. As we can see here, we show like a typical the optical transport network architecture. So you can see a lot of red triangles here, which represent the optical amplifier, the erbium-doped amplifier. So which is quite widely used in optical network. So if we step back to look at the history and also the principle of the erbium-doped amplifier, so the structure is pretty simple. So here you see, so erbium-doped fiber is basically the fiber doped with erbium ions in this medium. So once you combine the input signal and optical pump, and inject it into this amplifier, then the excited state of the ions can allow you to have stimulate the emission caused by the input signal. In the end, you have like amplified the signal from this the fiber output. Actually, this idea was already demonstrated in 1965, but based on like the glass rod using the rapid flash up lamps for the optical pumping. As you can see, some like absorption feature for the erbiums around the wavelengths of 1550 nanometers. So 20 years later, the first demonstration of the erbium amplifier was reported by Professor David Payne from Southampton University, and also the researcher Tesla Wire and the guys from Bell Labs. So this demonstration really showed the first like a erbium-doped fiber amplifier. So immediately, like a few years later, so researchers start to implement this fiber EDFA into like communication link, but at this stage is still using the very simple intensity modulation and the directed photo detection approach for this link. But this is already very impressive that it can allow you to transmit the optic signal over like even 300 kilometers, which is previously unachievable using other techniques. So here, let's have a look at the basic principle and the advantage of the erbium-doped fiber amplifier. I will start with like a very simple three-level energy diagram for the erbium ions. So you can use the optical pump at 1480 around 1480 nanometers, or you can use like a 980 nanometers pump. That depends on your application. So for example, let's stick to this case with 1480 nanometers pump. Now you can pump the excited wave, the erbium ions in the grounded state to the first excited state. And then you, on the other hand, you can have a spontaneous emission or a stimulated emission from 1550 nanometers. And so this, the erbium ions has a very unique electrical structure, which is the parity forbidden intro 4F shell transition that give you a millisecond long lifetime. So in the end, you have a very slow gain dynamics, and also in the end, you can have it's less sensitive to the faster transient, the amplitude of fluctuation, and also it allows you to have like a lower interchannel crosstalk, which is very attractive for the communication, in particular for the wavelength division multiplex of the communication. On the other hand, you also have a very good temperature stability and a low noise figure approaching to the quantum mechanical limit of 3 dB for the phase insensitive amplification. And compared to like semiconductor amplifier, it also has a very lower linearity and a two photon absorption. So, but actually the cases, so the principle for the erbium double amplifier is more complicated because when you, in particular, you have a very high concentration. For example, in this case, the erbium ions, the excited erbium ions can promote the other excited erbium ions to the line energy level, and so which is a so-called cooperative up conversion process. On the other hand, you also have the excited state absorption that also reduce your population for the excited the ions. So in the end, if you look at the rate equation that describes how the population is achieved, you can see there's a few terms responsible for the stimulated emission and optical pumping. On the other hand, you also have like contribution from the excited state absorption and the cooperative up conversion. So cooperative up conversion here. So let's say focus on the first order cooperative up conversion. So in this case, so it's proportional to the square of the population of the first excited level. So that means when you have like a larger population on the excited level, and this parameter can really limit your the performance for the high gain operation. Okay, in this case. So when we look at the light amplification for in the erbium-doped amplifier, then we can see the gain term that is related to the population inversion for the urban lines and also the propagation loss. So in order to maximize the gain over the entire waveguide, so we have to guarantee we have a larger population inversion, and also we need to minimize the propagation loss, which is also called background loss in this case. So for the open fiber amplifier, the EDFA has already also become like a very important element for the fiber-based laser, for example, the model of laser. So with the rise of the photonic integration technology, it's highly desirable to miniaturize the laser, the fiber-based laser onto the integrated platform. So in the end, we have the integrated laser, which gives you like a good compatibility, compactness and stability. And also for the model laser, we can have like a higher repetition rate because of the shorter on-chip at the cavity length. But however, this is very challenging because in order to achieve like a very high gain in the short or the centimeter scale photonic waveguide, you really need to reduce the optical loss and also guarantee you have like a high gain coefficient. However, this is usually limited by the erbium concentration, the erbium concentration you dope in this medium. Because like for the high concentration case, you have a larger cooperative upper conversion. So in that sense, you really limited your the gain coefficient in this case. So, well, finally, we also need to consider the compatibility for the integration with other platform, which is very important for the mass production. So when we step back to look at like a state of the art of the integrated waveguide optical amplifier, so we found that so the commercial erbium-doped fiber amplifier can typically give us more than 100 milliwatt output power. In the meantime, it can be operated in the high gain region, typically around the 30 dB. But if we look at the integrated amplifier recently, the heterogeneous integrated 3.5 amplifier has already gained a lot of interest in this field, and it promises can deliver a very decent amount of optical power for typically like a tens of like a milliwatt, and also can maintain a good gain. Although the fabrication complexity and the cost is pretty high. So actually, if we look back, like more than like 20 years ago, like people researchers have already looked into the erbium-doped the waveguide amplifier. So here it shows like the erbium-doped the glass waveguide with a cross section, where is a cross section with a core size of like a tenth of a micrometer wide, and typically it's fabricated by the ultra-fast laser inscription. So this is large like the large cross section will limit your compactness of your device, and it's not really compatible with contemporary silicon photonics fabrication. So in the recent like 10 years, people started looking into like erbium-doped like oxide materials such as erbium-doped aluminum oxide and telluride oxide waveguide. So you can use this like a GaN medium to form the waveguide directly. Then you have a very large overlap, the optical mode overlap with erbium ions in the waveguide. But again, so this device is not it also lacks the compatibility for the fabrication. So you can only use these for the standalone amplifier devices. So recently, the more interesting on integrating this like an open doped GaN medium in the CMOS compatible platform, for example, silicon nitride and the silicon waveguide. So for example, in this case, you can deposit uh, uh, deposit like erbium-doped aluminum oxide waveguide on top of the silicon nitride slot waveguide. So then the evanescent field in this cladding can experience the optical gain, or you can deposit as the GaN film on the second layer on top of the silicon nitride waveguide. However, the output power demonstrated in these platforms is typically limited to even less than 1 milliwatt. So this is typically limited to by the high background loss, and also the high cooperative upper conversion coefficient in this case. So as far as we can see, there's like a huge gap between the commercial EDFA performance and the integrated erbium-doped waveguide performance. Okay, so the major limitation for in this platform, as we said, is really the loss and the cooperative upper conversion in this case. So so except the optical loss. So here we just give a little bit more introduction to cooperative upper conversion process, which is like another gain limiting factor, in particular for the high concentration. So the idea is for this upper conversion is the excited urban lines can promote the other excited urban line to a high line level. Then you can then the population for the first excited state is reduced. Then we'll limit your population inversion and eventually limited your the achieved gain or the gain coefficient. So when you look at the previous achieved erbium-doped waveguide amplifier, so you can see most of the erbium-doped waveguide amplifier operator in this region typically have like a tens of dB per meter optical loss, and also has a relatively high as first order cooperative upper conversion coefficient. But if from the simulation, ideally you would like to have a waveguide with a propagation loss typically less than 10 dB per meter, and also a very low cooperative upper conversion coefficient. So in that sense, you can really achieve like a very high gain exceeding 30 dB and achieve like a 100 milliwatt output power. So in next like content, I will show you how we overcome these two challenges to achieve the lower loss in the tens of centimeter long waveguide, and also maintain a very low cooperative upper conversion coefficient typically for the first order upper conversion. And in the meantime, we can maintain a good overlap factor. So in this talk, I would start to show you how this active silicon nitride performance is implemented by the urban eye implantation technique. And then we show you how we operate this in the continuous regime, and also for the pulsar regime for the on-chip signal amplification. And in the end, we will provide our perspective for this research and the summary. So to start with this, the technical details here, I would like to recall the silicon nitride fabrication, so-called photonic damascene process developed by in EPFL. So instead of like etching the silicon nitride film directly, we pattern the waveguide into like small trenches or in the recess, which is also called the preform in this case. And then we deposit a silicon nitride film on top of this platform, then followed by the planarization process to achieve like sub-nanometers surface roughness. So before this platform step, we also have like a preform reflow to reduce the center wall roughness in this case. So in the end, we can conclude this fabrication by adding silica after cladding or not. That depends on the application. So in this, in the meantime, in order to get rid of like the stress the waveguide correct, so we use the stress release the pattern in this same platform to avoid this issue. So in the end, in this platform, we can achieve very thick silicon nitride waveguide with a well-controlled cross section. So that allows us to have very flexible dispersion engineering. In the meantime, this is in EPFL, this is process is compatible with a 4-inch wafer scale fabrication that allows us to have like a very low loss over the entire wafer. So for the best performance, we can even achieve like around the 6 dB per meter, 6 megahertz and intrinsic Q, so which is approaching the 1 dB per meter loss. So this really lays the foundation for our the work showed in the next few slides. In the meantime, so as we talked about before, in order to achieve like a erbium-doped waveguide amplification with a high gain, we really need to use a relatively long waveguide to make sure we can have like a large integral gain along this waveguide. Along this waveguide. So in this case, for we fabricated like the meter scale silicon nitride waveguide, typically with 0.1 meter and 1 meter, with a typical loss around 2 dB per meter. And we can achieve 1.7 dB per meter in the like shortest waveguide, which is 0.05 meter in this case. So this low loss platform really enables a lot of like application demonstration. For example, with this low loss, the high Q resonator, we can achieve narrow linewidth like a frequency agile laser, and we can generate the soliton microcomb with a low threshold power. And the generated soliton comb can be used for the LiDAR, for the massive parallel LiDAR ranging, and also microwave signal generation. And recently, we also demonstrated an optical parametric gain amplifier in the meter scale silicon nitride waveguide. In the end, you can be also integrated with a thin film silicon nitride film to implement a modulator. Okay, so in this work, we combine the silicon nitride damascene photonic process with the erbium ion implantation technique. So the difference is from the last of the process flow we showed in the previous slide is that in this case we don't add any silica cladding. So because this L-cladded sample allow you to have direct erbium ion implantation into this waveguide. Okay, and after that we use the high temperature annealing, typically more than 1,000 degrees, to have the loss and the damage recovery in these implanted samples. So for the erbium ion implantation, is a technique actually proposed, demonstrated 30 years ago by Bodo Pullman. So the idea is fairly simple. So the idea is that you use a high energy erbium ions beam to be injected into this waveguide. For example, in this case, we can inject the erbium ions from the top, from the L-cladded sample into this silicon nitride waveguide in this case. And we can optimize the beam energy, which corresponding to the different implantation depths, and also the concentration or the fluence for the erbium ions. So in this case, we use 3 different energy and a different concentration to engineer a widely distributed erbium distribution in this silicon nitride waveguide. So from the axis is actually from the top, so the vertical direction from the chip up to the bottom. So in the end, this largely widely distributed erbium ions distribution can have a very large overlap with the optical mode, which is a fundamental mode in this waveguide indicated by this red curve. So in the end, we can have a very large overlap factor approaching 50% in this case. So and we can achieve like a maximum the doping depth around 400 nanometers with 2M UV beam energy in this case. And we use like a RBS, the Roosevelt backscattering spectrometry, to verify the concentration to be well matched with the simulated concentration in this case. So after that, so we after this implantation, we immediately use like high temperature annealing process to recover the optical loss. For example, in this case, so the measured loss for the implanted sample has a relatively large background loss. It's around 1 dB per centimeter, which is like 100 dB per meter in this case. So it has a huge increase between the reference waveguide before the implantation, which is indicated by this like a yellow dot. So after the high temperature annealing, we can immediately reduce the background loss from the 100 dB per meter case to a single digit dB per meter in this case. If you look at this inset at around at the wavelength around 1600 nanometers, which is relatively away from the erbium absorption center. So in this case, we can even achieve like a 5 dB per meter waveguide loss, which is very important for the on-chip erbium amplifier demonstration. So once you have this waveguide fabricated and annealed, then we can inject the optical pump from both sides of this chip using the ultra high NA fiber in this case. So the reason why we use ultra high NA fiber here is because we want to get rid of this L gap between the chip facet and the fiber facet. And we apply the refractive index matching gel in the middle to get rid of the strong reflection, which will cause the parasitic lasing in this waveguide. And we can see, I mean, as we introduced before, the high order cooperative upper conversion can give you the green light emission. So then we use this green light emission, the intensity distribution along this waveguide, to try to get some intuition about the propagation loss for the pump. So in this case, we can see a relatively uniform distribution of this green light emission, which means the pump is not significantly attenuated along this waveguide. Okay, so in the meantime, you can maintain the relatively good population inversion along this waveguide. In order to determine the lifetime and the emission property of in this platform, we use a 980 nanometers pump, which is away from the emission center, so we can measure the clear emission spectrum of the erbium ions. So in this case, we measure the like a fluorescent lifetime around 3.4 milliseconds in this case. And then we use this equation to determine the emission cross-section, so which is not detailed in this case due to the time limit. So for the next step, then we embedded this sample into the experiment setup that allows us to have the bidirectional pumping. So we have two different pump laser generated from the two pump laser diodes, coupled in forward direction and in backward direction. And we send the probe laser, which is wavelength tunable and with control the power. So we can scan the wavelengths to get the broadband gain performance for this waveguide amplifier. So when we send in like a 0.1 milliwatt output power, output power, we can get more than 30 dB on-chip net gain for some wavelengths. And for the shorter wavelengths, the gain coefficient, the gain is slightly lower due to the erbium reabsorption in this 50 centimeter long waveguide. So in the meantime, the erbium implantation technique also allow us to engineer the concentration so that we can increase the concentration and use a shorter waveguide to achieve the similar performance in this case. And if we look at the performance at the 1550 nanometers, we can achieve like a 30 dB gain. And we can see here some like fluctuation on the gain measurement. This is simply because of the parasitic lasing caused by the chip facet reflection. So that's the reason why we use the refractive index matching gel to reduce this. But even though it's still the gain is too strong, so we still have a very strong parasitic lasing for this small input signal. And for the signal, if we increase the power, of course the gain will reduce. But in the meantime, we can get a larger output power without the parasitic lasing. So in this case, we get like more than 140 milliwatt on-chip output power for this sample. So in this sample, we experimentally measure the gain coefficient, net gain coefficient of 1.9 dB for the highest concentration in this case. So then if we step back to look at the state of the art, the Erbium-Doped waveguide amplifier, then we can see, so this work can actually fill the gap between the commercial EDFA and also with the Erbium-Doped waveguide amplifier technique. So in this case, and then we also compared the noise figure performance for this Erbium-Doped waveguide amplifier. We reached like the lowest noise figure of 7 dB in this case. However, this is limited by the input coupling loss and also the parasitic lasing. So with with a reduced reflection, we should be able to get a lower noise figure in this case. So in the last 5 minutes, I would like to, in the end, talk about how we make use of this waveguide for other applications, except that only the amplification of the CW signal. So with the recent like 10 years, we have really seen a lot of advancement in the photonic integration circuit technology. One of this advanced technology is the dissipative current soliton, so which allows you to use a single frequency laser to generate an optical frequency comb in the small ring resonator. And this dynamic is in the ring resonator with the current linearity described by this LA equation. So which is like a modified version of the nonlinear Schrodinger equation with a boundary condition. So it really describes the interplay of like dispersion on current linearity and loss and again in the static cavity. So when you operate this in the particular regime where you have the double balance between the anomalous dispersion and also the current linearity, as well as the loss and the parametric gain provided by the external laser, then you can form the solitary like a pulse inside this ring resonator on a CW the background. So in the frequency domain, is translated into the frequency comb with equally spaced the comb lines with a uh, uh, high coherence and a low phase noise. So however, the problem for this generated comb is that the power conversion efficiency from the pump is generally very low. It only probably give you like a 1% for a 200 gigahertz single state soliton generation. So for example, in this case, with a ring resonator, uh, with a ring resonator with a 20 gigahertz FSR, we can generate the repetition rate of around 19.6 gigahertz repetition rate with the input power of the comp power of 38 milliwatt. But the generated comp power can be much lower. It can be much less than 1 milliwatt. And then you have the additional coupling loss from the chip facet, then make the generator's comp power even lower. So this is unsure. So in order to make a use of this for application, for example, the photonic generation of microwave, then we always need the EDFA after the to amplify the generators the comp, so that to overcome this can so the amplified power amplified soliton can overcome the photon short noise in the photo detection. So, but the problem is, so the EDFA, the use of the EDFA will ultimately limit the miniaturization of this platform. And for example, the microwave signal generator. So in our case, we would like to apply our the Erbium-Doped waveguide amplifier to amplify the generator soliton from a separate chip. But this two platforms can be integrated on the same chip because it's also based on silicon nitride. So in this case, first we generated a single state soliton from the 20 gigahertz silicon nitride ring resonator. So we have a typical like the output power of around 0.08 milliwatts. And so then we send this generated frequency comb into this Erbium-Doped waveguide amplifier. We can achieve like an off-chip gain over 20 dB that can bring this optical power of the soliton to like a 10 milliwatt level. So, and we also, in order to benchmark the performance, we also use the EDFA, commercial EDFA to amplify at the same microcomb, which will give you a similar performance. And once we use the generator, the soliton microcomb, then we can use that to generate a low noise microwave. So in comparison with the soliton, the microcomb without amplification, we can see the higher Fourier frequency, the phase noise is typically limited by the short noise because the power is so low. Once you bring up this power to the 10 milliwatt level, then you can see immediate reduction in the phase noise for the the Fourier offset frequencies in this case. And the on-chip the Erbium-Doped waveguide amplifier shows the identical performance with the commercial EDFA. So another example
Sorry,
we show
we only have one
yes.
more minute.
Okay, so another example we show here is that we can make a use of this Erbium amplifier, Doped waveguide amplifier to amplify the microcomb for the previous demonstrated the optical communication experiment, because the optical frequency comm can give you a lot of like a optical carrier for the wavelength division multiplexing of the communication. But however, again, you really need the EDFA like before transmitting the data, and also the EDFA for the amplified for the amplification of the generated soliton. So again, this is very limited your miniaturization of your communication transceiver system. So again, here we generated a 100 gigahertz soliton from the separate chip. Then we send this amplified microcom into this WDM communication link, and we modulate each carrier with the 10 gigaport QPSK bit stream. And after transmitting over 1 kilometers transmission link, we can successfully demonstrate a reliable data transmission for more than 20 channels, and that can satisfy the BR, the requirement in this case. For the frequency, for this few channel with a larger bit error ratio, this is simply because the power is not high enough for the certain wavelength. Okay, so just to provide like a perspective. So again, this platform can be and this Erbium implantation can be applied to a more complicated silicon nitride platform. So then we can use a selective doping approach to selectively activate the GaN property in this silicon nitride platform without affecting the passive device structure. For example, in this case, we can still use these passive devices for the dissipative soliton generation, and then we can use this to combine the COM generation with amplification on the same platform, which allow us to have like tens of a milliwatt or even 100 milliwatt output power of the soliton. So on the other hand, we can implement the vernier laser, for example, to achieve the single frequency lasing. And we made a good progress to demonstrate this selective doping technique that allows us to have this the envisaged like
Sorry, Dr. Liu,
application.
we are out of the schedule.
Okay, so let me conclude this talk. Sorry for the delay.